Massive stone blocks were moved across impossible distances by people with simple tools. We are uncovering the operational methods behind large-scale, ancient quarrying efforts to solve this enduring mystery. By the end, you will understand the precise systems that built our world's most iconic monuments. How did thousands of workers coordinate without modern technology? What forgotten engineering secrets allowed them to split and transport mountains of stone? This journey reveals a story of brilliant organization hidden in plain sight. What does it truly take to reshape a landscape with nothing but human ingenuity? The sound of a hammer tapping against bedrock was the first test of destiny for a future monument. Ancient surveyors were not merely looking for stone, they were searching for perfection in the earth itself. They walked vast landscapes, their eyes trained to spot the subtle signs of a superior quarry site. A single hidden fissure or a soft vein of mineral could spell disaster, causing a multi-ton block to fracture during extraction or, worse, centuries later. So they listened intently. A clear, bell-like ring from a hammer strike indicated dense, solid stone, while a dull thud revealed internal flaws. They studied the color and the grain, understanding that the very character of the rock would determine if it could become part of a pyramid or a column meant to last for millennia. This was a decision of profound consequence. Choosing the right location was the cornerstone of the entire endeavor. A perfect seam of limestone might lie miles from a river, adding immense complexity to its transport. A granite deposit on a steep hillside presented its own set of challenges for moving colossal weights. Every choice involved a trade-off between material quality and the staggering logistics of what came next. The site selection locked in the fate of thousands of workers and the ultimate success of the project, long before the first innovative tools were ever deployed to break the earth. With a perfect stone identified, the real challenge began, prying these colossal blocks from the earth's grasp. Ancient quarriers mastered a subtle art of persuasion, using the stone's own weaknesses against it. One of the most widespread methods relied on a simple combination of wood and water. Workers would locate natural fissures in the bedrock and carefully carve a line of slots. Into these slots they drove dry wooden wedges. Then they soaked the wood. As the wedges absorbed the water, they swelled with immense, relentless force. This controlled pressure would then cleanly split the massive stone block along the desired line, a testament to understanding the hidden strengths and vulnerabilities within the rock itself. This technique, seen from Egypt to Mesopotamia, was not brute force. It was a precise science. The quarriers had to possess an intimate knowledge of the stone's grain and internal structure. Striking at the wrong angle or using too much force could shatter a priceless block into worthless rubble. They learned to work in harmony with the material, often following the natural bedding planes in sedimentary rock, much like a carpenter follows the grain in a piece of wood to split it cleanly. Once freed, the blocks were not yet finished. They were rough-shaped right there at the quarry site, skilled workers knocking off excess stone to reduce their weight for the monumental journey ahead. This entire process, from the swelling wood to the final rough cut, reveals a sophisticated, almost intuitive grasp of material science. It makes you wonder what kind of tools could perform such precise work on such an unforgiving canvas. But persuasion through water and wood was only one part of their toolkit. For the hardest stones, like granite, quarriers turned to an even more durable material, dolerite. These hammerstones, themselves a form of incredibly tough rock, became the primary instruments for confronting a mountain. Workers would pound these hammerstones relentlessly, not to smash the granite, but to pulverize it grain by grain. They would create a deep channel or a series of closely spaced holes around the perimeter of a massive block, effectively isolating it from the living bedrock. This was a monumental task of patience and endurance, a testament to human persistence. Once the block was sufficiently undercut, teams would insert wooden or bronze levers into the channels, using coordinated force to prise the colossal stone free from its ancient home. For softer stones like limestone, a different technology emerged. Copper and bronze chisels, those softer and requiring constant resharpening by attending craftspeople, allowed for more precise cutting and shaping. The real leap forward came with the Romans and their mastery of iron. Iron tools were stronger, held an edge longer, and revolutionized the speed and efficiency of quarrying operations. Yet the true sophistication lay not in any single tool, but in their orchestrated use. Teams of workers had to coordinate their strikes with rhythmic precision, creating uniform fractures along a line that could stretch for dozens of feet. This was a form of music, a percussive symphony conducted to break solid rock. The constant evolution of these tools, from stone to copper to iron, was not driven by abstract science, but by the relentless demands of practical necessity. It was this drive for efficiency that inevitably shaped the most complex element of all, the human machine required to wield these tools on an unimaginable scale. The percussive symphony of stone on stone required a conductor, a mind capable of orchestrating thousands of hands. Beyond the brilliant tools lay the true marvel, the human machine. Large-scale quarrying was a monumental organizational challenge, a puzzle of logistics and management that rivaled the engineering itself. At remote sites like the Roman quarries at Mons Claudianus, archaeologists have uncovered evidence of a highly structured society carved into the desert rock. A clear hierarchy governed every action. Skilled foremen, often master stonemasons themselves, directed teams of laborers. These teams were meticulously divided by specialty. Some crews focused solely on the initial extraction, wielding the heavy hammerstones to isolate blocks. Others, with a more delicate touch, handled the rough shaping of the stone right at the quarry face. Another group would be dedicated to preparing the blocks for their journey, smoothing bases or carving lever points. This precise division of labor was the key to continuous, efficient operation. It meant that no single team waited on another, creating a relentless flow of stone from the mountain. The workforce itself was a complex tapestry. It included highly skilled artisans, unskilled day laborers, and, in many ancient societies, individuals who were enslaved or soldiers conscripted for the task. Managing such a large and varied group in a harsh, remote environment required systems that feel remarkably modern. Surviving records from Egyptian and Roman sites detail work schedules, careful distributions of food and water rations, and even notes on medical care for injuries sustained on the job. This was not merely about issuing commands, it was about sustaining a miniature city in the wilderness, ensuring the well-being, for purely practical reasons, of the human capital that powered the entire operation. This sophisticated approach to workforce management reveals that the ancients understood a profound truth, that a project's success relied as much on the health and coordination of its people as on the strength of their tools. And keeping this remote, organized army supplied created a logistical challenge of its own, a relentless river of needs flowing into the desert. Freeing the stone from the mountain was only half the battle. The true test of ingenuity began the moment a multi-ton block was pried loose, now needing to travel miles across unforgiving terrain. Moving these colossal weights required a logistical ballet of brilliant simplicity and overwhelming coordination. For land transport, the solution was often a reinforced sledge, a massive wooden platform dragged by teams of laborers. But the real secret was not in the pulling, it was in the path. Workers would create a temporary trackway, sometimes lubricating the ground with water or wet mud to dramatically reduce friction. This simple trick transformed an impossible haul into a manageable, albeit back-breaking task. Tomb paintings from ancient Egypt show this very process in action, depicting long lines of workers, ropes taut over their shoulders, hauling a giant statue on a sledge as a person at the front pours water onto the pathway. It was a system that turned human sweat into a fluid, sliding force. When the destination was far away, water became more than a lubricant, it became the highway. The ancients universally preferred to move their heaviest cargo by boat. In Egypt, quarries were often linked to the Nile by specially dug canals. Blocks were loaded onto massive, wide barges. The timing was everything. They would wait for the annual flood when the river swelled and its currents could help carry the immense load. This was a perfect synchronization with nature's own calendar, using the planet's cycles as a powerful engine. The Romans, masters of infrastructure, expanded this concept. They built extensive networks of roads capable of supporting incredibly heavy transport, sometimes employing enormous ox-drawn carts for shorter overland journeys between a river and a construction site. Each method, from slick track to river barge, required a deep understanding of physics and precise timing. But this entire logistical chain hinged on a single, critical moment of engineering: the perilous transfer of the stone from solid ground onto a waiting vessel. How do you safely lower a piece of a mountain onto a floating platform without sinking it? The solution required another layer of brilliant, simple innovation. The most perilous moment in the stone's journey was the transfer from solid ground to a waiting barge. One wrong move, one misjudgment of weight, and a priceless obelisk could plunge to the riverbed or crush the very vessel meant to carry it. To conquer this challenge, ancient engineers designed sophisticated loading systems that turned brute force into controlled, deliberate motion. The most common solution was the earthen ramp. Workers would construct a massive, gently sloping embankment of packed earth and rubble, leading right down into the water and up to the deck of a heavily reinforced barge. This ramp provided a stable, continuous path, allowing teams to carefully slide or roll a block directly onto its transport. The true genius, however, lay in the control mechanisms. Using a complex arrangement of ropes, levers, and wooden rollers, they could inch the multi-ton block downward with painstaking precision. In some quarries, you can still see the remains of permanent stone slipways, grooves worn into the bedrock by countless blocks making their final slide into the water. For lifting operations, particularly in Greek and Roman eras, a more advanced technology emerged: the treadwheel crane. This was a wooden framework housing a giant, human-powered wheel. Workers would walk inside the wheel, much like a hamster in a cage, their collective weight and movement providing the power to operate a rope and pulley system. This machine allowed for the vertical lifting of heavy stones, enabling builders to load blocks directly onto high-sided carts or position them with incredible accuracy. Every one of these methods, from the simple ramp to the complex crane, was a practical application of physics. The engineers had to intuitively understand balance, leverage, and the distribution of weight to prevent catastrophic failure. They were not just moving stone, they were performing a delicate ballet with massive forces, a testament to their ability to innovate under immense pressure. This same innovative spirit was absolutely essential for solving a more fundamental problem: how to provide life-giving water to these remote, arid work sites in the first place. Yet this life-giving water was far more than just a highway for transport. It was a versatile and powerful tool in its own right, a silent partner in the quarrying process itself. Ancient workers mastered the art of using water to do their most difficult work for them. To keep their cutting tools sharp and effective, they constantly poured water over the cutting surface. This simple act served as both a lubricant and a coolant, reducing the intense friction that would otherwise quickly dull a copper chisel or shatter a hard dolerite hammerstone. This extended the life of their precious tools and made the grueling work of carving through stone markedly more efficient. In regions with colder climates, quarrymen discovered an even more forceful application for water. They would intentionally channel it into narrow, pre-cut fissures in the bedrock. When the temperature dropped overnight, the water would freeze. As it turned to ice, it expanded with incredible, irresistible pressure, cleanly fracturing the stone along the desired line. This clever technique, harnessing the natural force of expansion, allowed them to split massive blocks with minimal effort, simply by letting the winter cold do the heavy lifting. Beyond the extraction itself, water was crucial for managing the work environment. The constant hammering and chiseling created thick clouds of fine, abrasive stone dust that choked the air, posing a health challenge for the workers and obscuring their vision. By regularly wetting down the worksite, they suppressed this dust, clearing the air and making the arduous conditions slightly more manageable. This focus on the work environment reveals a pragmatic understanding that the well-being of the workforce was directly tied to the project's overall pace and success. Managing water was a two-sided challenge, however. While they used it as a tool, they also had to fight against it. Groundwater seeping into a deep quarry pit could halt all work, turning the floor into a muddy bog. The solution was sophisticated hydraulic engineering. Archaeologists have found evidence of intricate drainage systems carved directly into the quarry floors. Networks of narrow channels would funnel unwanted water away from the active faces into deep, hand-dug sump pits from where it could be manually bailed out. This constant, silent battle to control water, to both harness its power and mitigate its intrusion, showcases a deep, adaptive intelligence. It was this same sharp intellect that guided the very first step of the entire operation, a skill that required seeing the invisible structure hidden within a solid mountain of stone. That final step of marking the stone required an eye that could see the future monument within the raw bedrock. Before a single hammerstone fell, the rock face had to be transformed into a precise blueprint. Ancient surveyors approached this task with tools of elegant simplicity, their accuracy born from a deep understanding of geometry and physics. The groma, a clever Roman instrument, consisted of a cross-shaped frame with plumb bobs hanging from each arm. By sighting along the weighted lines, a surveyor could establish perfectly perpendicular lines across a vast quarry floor, mapping out the grid from which thousands of uniform blocks would be born. For ensuring a level surface, they relied on the chorobates, a long wooden bench with a central groove. They would fill this groove with water, and when the surface was perfectly still, they knew the instrument was level. This allowed them to transfer a true horizontal plane across the uneven ground, a critical step for ensuring that the bases of future columns and walls would be stable. This precision was then transferred directly onto the stone itself. Using ochre paint or shallow chiseled grooves, workers marked the exact dimensions of each block on the quarry face. In some Egyptian quarries, you can still see faded red grid lines painted on the walls, a ghostly reminder of the meticulous planning that preceded the extraction. These grids, often based on standardized units like the royal cubit, acted as a giant stencil, guiding the stone cutters to produce blocks that were nearly identical in size. This system of pre-planning was the key to efficient assembly at distant construction sites. When a block arrived after its long journey, it needed minimal additional shaping to fit perfectly into its designated place. The time saved by this foresight was immense, turning a chaotic pile of stone into a cohesive, interlocking structure. The true marvel is that this precision was achieved across continents and cultures, all without a single digital reading. It was a testament to the power of shared knowledge and meticulous technique. How did this deep understanding of measurement and geometry, so vital to quarrying, influence the very organization of the workforce itself? And what does the layout of a quarry reveal about the minds that designed it? That meticulous eye for measurement was built upon an even deeper foundation, a profound understanding of the very earth they were cutting into. Ancient quarriers were practical geologists, their knowledge earned not from textbooks but from generations of hands-on experience. They learned to read a cliff face like a map, identifying the most valuable layers of stone hidden within. The most prized rock was often found deeper down, in compact strata that had been protected from the weathering effects of wind and rain. These unweathered layers offered superior strength and consistency, the perfect raw material for a monument meant to endure for ages. In the legendary marble quarries of Carrara, Roman engineers did not simply dig randomly. They became experts at tracing specific veins celebrated for their pure white color and fine grain, a quality that made their sculptures and buildings gleam in the sun. Their survival depended on recognizing and avoiding flaws. A visible streak of quartz or the telltale sign of an ancient fossil could create a hidden weakness, a fault line that might cause a multi-ton column to crack under its own weight years after it was erected. This was a craft passed from master to apprentice, a cumulative science refined over centuries. This deep material knowledge directly dictated how different stones were used. Builders consistently selected softer, more workable limestone for the vast core blocks of a pyramid, where it would remain unseen, while reserving incredibly hard granite for facing stones and obelisks that had to withstand the elements. This nuanced appreciation for material properties even influenced the timing of their work. Quarrying the hardest stones was often a seasonal activity, planned for cooler months when working conditions were less arduous and the stone itself might behave differently. Every decision, from which layer to exploit to when to swing the hammer, was a calculated choice rooted in an intimate, generational dialogue with the landscape. This rhythmic dance with the seasons was a cornerstone of ancient logistics. Quarrying was not a constant, year-round assault on the mountain, but a carefully timed campaign synchronized with the natural world. In Egypt, the entire operation revolved around the life-giving pulse of the Nile. The annual flood which submerged the fields created a paradoxical opportunity. It freed a massive agricultural workforce from their land, making thousands of laborers available for state projects. At the very same time, the swollen river turned into a natural superhighway, its elevated waters allowing heavily laden barges to travel with ease. The quarrying season became a burst of intense activity, perfectly aligned with this narrow window of available labor and ideal transport conditions. In temperate regions, the calendar was dictated by a different adversary, the weather. The deep cold of winter could make work unbearable and even dangerous. Water used for lubrication would freeze, halting progress, and working with metal tools in freezing conditions was impractical. Heavy autumn and spring rains could turn quarry floors into treacherous mud pits and obscure the vital markings on the stone. Therefore, the clear, dry days of summer were often the preferred time for large-scale extraction. This cyclical pattern created a natural rhythm of production and stockpiling. During the active season, workers would focus on extracting and rough shaping as much stone as possible. These blocks would then be gathered in vast stockyards near the quarry or at loading ramps, creating a reserve of material that could be drawn upon throughout the year by construction crews at distant temple or pyramid sites. This system required remarkable foresight. Planners had to estimate the needs of projects years in advance, ensuring that enough stone was quarried in a few productive months to sustain building efforts during the off-season. It was a masterclass in long-term resource management, a testament to an administrative mind that could think in cycles and seasons. This stockpiled stone, however, was not yet ready for the builder's hand. Each block had to undergo a crucial transformation right at the quarry face, a preliminary shaping that balanced the need for precision with the immense difficulty of moving its colossal weight. The moment of separation was a controlled fracture, not a chaotic break. With the block precisely outlined on the quarry face, workers would begin the delicate work of undercutting. Using hammerstones and chisels, they painstakingly carved a horizontal channel beneath the future block, effectively isolating it from the living bedrock and creating a predefined plane of weakness. This undercut was the key to a clean release. Then, teams would carefully insert wooden or bronze wedges into the narrow gap. A coordinated series of taps, sometimes with heavy wooden mallets, would send vibrations through the stone. The force was not meant to smash but to persuade, encouraging the block to fracture cleanly along its natural grain and break free from the mountain with a deep, resonant crack. Once liberated, the multi-ton stone was far from finished. The primary shaping began immediately, right there at the foot of the cliff. Skilled workers wielding stone mauls would systematically knock off the most prominent protrusions and jagged edges. The goal was not a perfect finish, but to create relatively flat surfaces that would not snag during transport. This rough dressing served a crucial purpose. It dramatically reduced the block's overall weight. By removing excess stone before the journey even began, they were saving immense effort at every subsequent stage, from hauling to loading. Walking through an ancient quarry today, you can witness this process frozen in time. Partially extracted blocks remain eternally trapped in the rock, some just outlined in paint, others fully undercut but never pried loose. These silent sentinels show us the step-by-step methodology, a visible record of the quarryman's craft. This focus on minimizing waste at the source was a hallmark of their efficiency. Even the rubble created from this rough shaping was rarely discarded. Smaller, irregular pieces were often gathered for use in roadbeds as fill inside walls or for local construction. Nothing was wasted if it could be used, a principle of resourcefulness that turned every fragment of the mountain into a potential asset. The mountain was not merely a source of stone, it was a complete resource to be used with profound economy. In the sprawling quarries of the ancient world, the concept of waste was almost non-existent. Every fragment of rock, from the grandest block to the smallest chip, held potential value. The larger offcuts and irregular pieces deemed unsuitable for primary construction were never simply discarded. Instead, they were gathered and repurposed as essential rubble fill, packed into the cores of massive walls or pyramids to provide stability and reduce the need for perfectly cut masonry. This practice was both practical and ingenious, turning what might have been refuse into a vital structural component. Even the smallest flakes and chips found a second life. They were often collected and heated in kilns to produce lime, a key ingredient in the mortar that bound stones together. In some cases, the fine stone dust created by endless hammering and chiseling was carefully swept up and mixed into plaster, giving walls a smoother finish. This relentless recycling extended beyond the stone itself. Broken or blunted metal tools, far too valuable to abandon, were gathered and sent to on-site smithies. There, the metal was reheated, reworked, and reforged into new chisels or wedges, completing a closed loop of material use. At large imperial quarries, archaeologists have studied what might initially appear to be simple trash piles. These systematic spoil heaps reveal a surprising order, with different types of debris sorted and placed in specific areas. This indicates a thoughtful approach to disposal, ensuring that usable material remained accessible and the work site itself stayed clear and safe for the thousands of laborers. This holistic view of resource management speaks to a deeply ingrained sustainability. Their operations were not a reckless plundering of the landscape, but a calculated, long-term partnership with it, supported by the sophisticated infrastructure that made such meticulous organization possible. This careful orchestration of every resource, from the grandest block to the tiniest shard, demonstrates that their true genius lay not just in moving mountains, but in ensuring that not a single piece of that mountain was ever truly lost. The quarry itself became a living, breathing settlement, a city carved from necessity at the foot of a vanishing mountain. Beyond the dust and the din of extraction lay a meticulously planned support system, an infrastructure designed to sustain human life and logistical flow for generations. The most immediate need was shelter. Vast barracks, often simple stone structures with sleeping platforms, housed the thousands of laborers. Nearby, more substantial administrative buildings stood as the project's nerve center. Here, scribes meticulously recorded every block extracted, every tool issued, and every ration distributed, their papyrus scrolls forming the bureaucratic heartbeat of the operation. Storage facilities were equally vital, safeguarding precious metal tools, food supplies, and spare parts for the transport sledges and carts. In the harsh environment of the Egyptian Eastern Desert, this entire complex was sometimes encircled by fortified walls. These were not just defenses against potential conflict, but a practical measure to protect both the workforce and the immensely valuable cut stone from any form of disruption. The presence of small worship areas or shrines speaks to another profound need. These spaces provided spiritual solace and a sense of community, a reminder of home for men who might spend years toiling in this remote, industrial landscape. This transformation from a simple worksite to a permanent industrial town represents a staggering investment. It signifies a commitment measured not in seasons, but in decades, even centuries. A temporary camp would not warrant such fixed, durable construction. This was capital investment on a grand scale, a clear declaration that the flow of stone was essential to the state's identity and power. Keeping this remote city supplied and functional required a web of internal infrastructure as clever as the extraction methods themselves. A network of carefully graded roads and ramps crisscrossed the quarry floor, allowing teams to move men and materials efficiently between the active faces, the workshops, and the loading areas. But the most critical resource in a desert environment was water. Engineers constructed large, plaster-lined cisterns to capture and store precious rainwater. This water was not for grand hydraulic projects, it was for survival. It quenched the thirst of the workforce and was constantly poured over cutting tools to keep them cool and effective. Every element, from the road underfoot to the water in the cistern, was part of a single, integrated system. This level of permanent organization points to a sophisticated administrative machine operating behind the scenes, one capable of managing not just the stone, but the very human ecosystem required to wrest it from the earth. These administrative systems were the invisible architecture behind every stone. In the dust-filled offices of an Egyptian quarry, scribes did not use precious papyrus for daily notes. They wrote on ostraca, broken pieces of pottery or limestone flakes, inscribing the pulse of the operation in ink. One fragment might record the issuance of 20 bronze chisels to the crew working the northern face. Another would list the exact bread and beer rations distributed to a specific work gang, a practical system ensuring every man was fed and accounted for. These were not simple memos. They were the living data stream of the quarry, a real-time log of productivity, resource allocation, and human need. This meticulous tracking allowed foremen to pinpoint bottlenecks, prevent theft of valuable metal tools, and maintain the relentless rhythm of extraction. The Romans elevated this record-keeping into an empire-wide tracking system. As a block was rough-shaped, a worker would carve a series of letters or symbols into its side. These quarry marks were like an ancient barcode. They could indicate the specific team that extracted the stone, the consular year it was quarried, or even the imperial project it was destined for, like the Pantheon or a distant frontier fort. This created an unbroken chain of custody from the mountain to the monument. If a block cracked during transport, administrators could trace it back to its source and even identify the responsible work crew, enforcing a powerful form of quality control. This data flowed upward to a central administration. In Rome, a dedicated imperial bureaucracy coordinated the output from quarries stretching from Egypt to Turkey, matching the supply of colored marble and granite to the demands of colossal construction projects hundreds of miles away. They managed a stone pipeline across the entire Mediterranean. These records also served a higher financial purpose. The volume of stone extracted was directly tied to taxes and tributes owed to the state or the pharaoh. Every block had a value, and every ostraka was a line in a ledger that accounted for wealth literally carved from the earth. The sheer existence of this detailed paperwork underscores a profound truth. Quarrying was not a side project. It was a core industry, a primary driver of the ancient economy that required a managerial class as sophisticated as any in the modern world. The quarries at Aswan are a testament to granite's stubborn beauty, a landscape permanently marked by the ambition of pharaohs. Here, the scale of operation was breathtaking. Workers did not fight the stone's natural character, they studied it. They identified the natural fracture lines known as joints that ran through the pink granite, and they used these inherent planes of weakness as their starting guide. To isolate a future obelisk, they would carve deep, narrow trenches directly following these joints, physically separating the monolith from the bedrock on all sides except one. Then teams wielding dolerite pounders, round balls of the same incredibly hard stone, would begin the grueling work of undercutting. For weeks, perhaps months, they would swing these heavy pounders in a steady rhythm, pulverizing the granite grain by grain to create a hollow beneath the colossal block. The evidence of this painstaking process is still visible, etched into the very floor of the quarry. The famous unfinished obelisk, which would have been the largest single piece of stone ever attempted by the Egyptians, remains partially attached to the bedrock. It is a frozen moment in time, a three-dimensional blueprint showing the trenches, the undercutting, and the sheer audacity of the endeavor. A single crack discovered deep within the stone ultimately caused its abandonment, a stark reminder of the high stakes and the unforgiving nature of the material. Once successfully freed, the challenge shifted from extraction to movement. How do you transport a needle of stone weighing over 1,000 tons? The answer flowed right past the quarry. The Nile was their conveyor belt. Specially designed barges, colossal vessels of cedar and acacia wood, were built with a hull strength that defies belief. When the annual floodwaters rose, these boats were maneuvered into canals dug right up to the quarry's edge. The obelisk was then carefully inched onto its floating cradle, a logistical ballet we discussed earlier. The river did the heavy lifting, carrying these symbols of divine power northward to their final homes in Thebes and Heliopolis. This Egyptian mastery of both material and logistics set a powerful precedent. Their methods demonstrated that with precise observation and coordinated labor, even the hardest stone could be made to obey. This legacy of systematic extraction did not fade. It traveled across the sea, where another civilization would refine the art of quarrying for a different kind of perfection, one defined by light and shadow. The Greek approach to marble was not merely functional, it was a pursuit of light itself. On the sun-drenched slopes of Mount Pentelicus, quarriers sought a stone that would do more than just stand, it would glow. Their primary innovation was a simple but profound shift in technique. Instead of just working from a single cliff face, they carved deep, narrow trenches directly into the mountain's surface. This trench method allowed teams to access a block from all sides, prying it free with iron levers from a platform of solid rock rather than an unstable pile of debris. This produced blocks with cleaner, more precise edges, a crucial quality for the intricate joints of the Parthenon. But the true genius lay in their eye for the material itself. They were not just quarrying marble, they were curating it. In the legendary quarries on the islands of Paros and Naxos, workers became connoisseurs of crystalline structure. They learned to identify specific veins celebrated for their pure white color and a unique translucency that allowed light to penetrate the stone's surface, giving their sculptures a lifelike, almost breathing quality. This was a radical departure from simply finding the strongest rock. The very purpose of the stone, whether for a goddess's robe or a temple column, dictated which part of the mountain was exploited. This relentless focus on aesthetic perfection drove technical refinement. The need for flawless blocks demanded better tools and more precise extraction, leading to an upward spiral of quality and skill. The legacy of this Greek pursuit is visible in every sunlit curve of a classical statue, a testament to a civilization that saw in raw stone a potential for divine radiance. This artistic and technical inheritance would not be lost, but was instead absorbed by an empire that valued scale as much as beauty, setting the stage for an industrial revolution in stone. The Roman hunger for stone transformed quarrying from a local craft into a global industry. Their empire became a single, sprawling marketplace for rock, with imperial agents sourcing granite from Egypt, marble from Greece and Turkey, and even distinctive green stone from the mountains of Greece. This was not random collection, it was a state-managed system designed for one purpose: to funnel the symbolic wealth of the world back to its capital. At the heart of this system were quarries like Mons porphyrites in the Egyptian desert, the sole source of a deep purple stone called porphyry. This material was so rare and difficult to extract that its use was decreed by law, reserved exclusively for imperial monuments and statues of the emperor himself. Owning a piece of this stone was illegal for a private citizen, a powerful statement that the very earth beneath their feet belonged to Rome. To manage this colossal flow of material, the Romans imposed a powerful tool of efficiency: standardization. They developed a system of standard block sizes, much like modern bricks, though on a monumental scale. A legionary fortress in Britain and a temple in North Africa might be built with identically sized blocks of local stone, all following the same Roman specifications. This meant that construction crews, often soldiers, knew exactly how to handle and place every piece, dramatically speeding up the building process from one end of the empire to the other. This logistical miracle was made possible by the Roman mastery of infrastructure. They built a network of all-weather stone-paved roads that could support the immense weight of ox-drawn carts carrying stone from inland quarries to ports. Once at the coast, the blocks were loaded onto the great merchant ships that plied the Mediterranean, their hulls heavy with cargoes of marble and granite destined for the Eternal City. The entire system was a circulatory network, with stone flowing like blood through the empire's veins, all directed by a central administrative heart in Rome. This relentless demand for efficiency drove innovation in the quarries themselves. Roman engineers refined lifting technology, creating more powerful cranes powered by treadwheels. These machines allowed smaller teams to maneuver heavier blocks, increasing productivity and reducing the sheer physical toll on the workforce. The sheer scale of their ambition is etched into Rome itself. Just consider the Colosseum, a structure that required a precise, unending convoy of stone arriving from multiple quarries for years on end. Travertine from Tivoli, tufa from nearby hills, and imported marble for the seats and decorations all had to arrive on schedule, a symphony of coordination across vast distances. The methods perfected in these imperial quarries were so effective that they did not vanish with the empire. They were preserved in engineering manuals studied by medieval builders and adapted for the cathedrals of the Middle Ages, creating a direct technological lineage from the Roman quarry foreman to the master masons of a new era. The colossal Roman quarries fell silent, their administrative networks fraying like old rope, yet the knowledge of stone did not vanish. It retreated into the hands of local craftsmen, becoming a more intimate craft focused on the needs of the rising church. Medieval builders often returned to the very quarries the Romans had opened, not to extract mountains of stone for an empire, but to carefully select blocks for a cathedral rising in a nearby town. They adapted the old trenching methods and levering techniques, scaling them down for projects that prized spiritual grandeur over imperial scale. A key innovation began to hum beside these sites, the quarrying saw. This was a long, flat blade of iron, its teeth set with abrasive sand that could be drawn back and forth by teams of men. In some advanced regions, this demanding labor was augmented by the power of a water wheel, using a crank to transform the river's current into a relentless, grinding cut. This allowed for thinner, more precise slices of stone, reducing waste and enabling the intricate tracery and delicate carvings that define Gothic architecture. The guardians of this evolving craft were the guilds, powerful associations of stonemasons who controlled the trade secrets. They passed down their specialized knowledge through a strict system of apprenticeship, from apprentice to journeyman to master. A master mason could read a block of limestone like a book, knowing just how it would behave under the chisel and precisely where it should be placed in a soaring vault. While the monolithic ambition of the pharaohs was a memory, the medieval period perfected a different kind of majesty, one of light, height, and breathtaking detail. This era became a vital custodian of classical technique, a quiet bridge that carried the essentials of stonework through the centuries, carefully preserving them until a new age of invention was ready to build upon them once more. For centuries, the fundamental rhythm of the quarry remained unchanged, a slow dance between human muscle and unyielding stone. The core toolkit of hammer, chisel, and wedge saw only incremental refinement over thousands of years. This technological stability was not a sign of stagnation, but a testament to the sheer effectiveness of these perfected methods. They had solved the essential puzzle of extraction so elegantly that little needed to be added. This long era of continuity is a gift to modern researchers, who can use experimental archaeology to reconstruct these ancient techniques with startling accuracy. By carving trenches with replica dolerite hammers or splitting limestone with wooden wedges, they experience the process firsthand, timing the work, measuring the effort, and gaining a visceral understanding of the skill and patience required. These experiments confirm that the ancient methods were not just possible, they were often the most efficient solution given the materials and energy sources available. This deep continuity was finally shattered by the introduction of a new, violent force. In the early modern period, miners began using gunpowder for blasting. This innovation dramatically accelerated extraction rates, allowing workers to fracture massive sections of rock face in a single, thunderous moment. But this new power came at a cost. The uncontrolled explosions created immense waste, shattering as much stone as they freed and leaving behind landscapes of fractured, often unusable rubble. The true revolution, however, arrived with the age of steam. The Industrial Revolution brought steam-powered channeling machines and derrick cranes to the quarry floor. These machines did not just make the work faster, they fundamentally altered the relationship between worker and stone. Human strength was amplified by mechanical power, shifting the primary role from relentless pounding to the skilled operation of machinery. This transition from muscle to machine opened a new chapter, enabling the scale of modern construction, but also closing a long, intimate chapter in human history where the conquest of stone was a direct physical dialogue. The true test of ancient methods comes not from old texts, but from the sound of a modern hammer striking stone. Experimental archaeology bridges the gap between theory and reality, putting replica tools into the hands of researchers to see if the old ways truly work. Teams of historians and skilled stonemasons venture to abandoned quarries, armed with dolerite pounders, copper chisels, and carefully dried wooden wedges. Their goal is not just to observe, but to perform, to recreate the exact conditions of an ancient extraction from start to finish. In one remarkable experiment, a team carved a series of slots into a granite face, drove in their wooden wedges, and began to soak them. For hours, nothing seemed to happen. Then, with a sharp crack that echoed across the quarry, the entire block split cleanly along the intended line. The force exerted by the swelling wood was immense, yet the process itself was quiet and controlled, proving that this was not a myth but a highly effective, almost gentle form of persuasion. These reconstructions reveal the hidden nuances of the craft, the precise angle of a hammer strike, the rhythm of a team working in unison, the exact amount of water needed to swell the wedges without softening the surrounding stone. These are details that no ancient manuscript could fully capture. They demonstrate that the physical effort, while immense, was secondary to the profound understanding of material behavior. A modern worker with a steel sledgehammer might deliver more raw force, but without the ancient quarrier's knowledge of the stone's grain and fracture points, that force is often wasted, resulting in shattered rubble instead of a perfect block. This hands-on research offers a tangible, almost personal connection to the individuals who mastered this craft millennia ago. You feel the vibration of the hammer in your own arms, you see the slow, deliberate progress, and you gain a newfound respect for the coordination and silent communication that must have flowed between teams. It verifies that the accounts left by historians like Pliny the Elder were not mere exaggeration, but documented observations of a sophisticated and refined technology. These experiments do more than just confirm what we suspect. They often challenge our assumptions, forcing us to reinterpret the archaeological evidence with a deeper, more practical understanding of the human effort behind every stone. The silent walls of an ancient quarry speak through the scars left upon them. Every groove and fracture is a fossilized moment of human effort, a permanent record of the tools and techniques that once echoed through this space. Archaeologists approach these surfaces like detectives at a crime scene, meticulously reading the story etched in stone. The most common marks are the shallow, parallel grooves left by bronze or iron chisels. The spacing and depth of these grooves can reveal the size of the chisel used, while their remarkable consistency across a wide area points to a highly organized team, each worker striking with a shared rhythm and force. This uniformity is the signature of a disciplined workforce, a system where every swing of the hammer was part of a larger, coordinated plan. Sometimes the story is told not by what is present, but by what is absent. A perfectly smooth, sheer face on one side of a massive block, standing right beside a rough, heavily worked surface, provides a crucial clue. That smooth face is often a natural fracture plane, a pre-existing weakness in the bedrock that the quarriers cleverly exploited. They recognized this gift from the earth and worked alongside it, using their tools only to persuade the stone to break along that perfect, natural line. This saved immense labor and produced a cleaner block, showcasing their deep, intuitive geology. The direction of the tool marks can even hint at the individual workers themselves. A consistent angle of strike on a particular section might indicate a crew of predominantly right-handed individuals, a small but humanizing detail emerging from the stone. This forensic analysis builds a comprehensive picture of the quarry's workflow. By mapping the density and type of marks from the initial extraction point to the final dressing area, researchers can trace the block's journey and pinpoint the various specialized workstations within the site. This physical evidence acts as a vital check against written records. It confirms the tools described in ancient texts were actually used in the way the texts suggest, and it often reveals local variations and improvisations that official records would never bother to note. Every chip and scratch is a direct connection to the person who made it, a voice from the dust reminding us that these were not anonymous laborers, but skilled individuals whose collective effort, one deliberate strike at a time, literally moved mountains. Behind every perfectly split block of stone was the immense effort of the human hands that freed it. The breathtaking scale of ancient quarrying rested upon a complex and often difficult social foundation, a world where human lives were the primary fuel for these engineering marvels. The workforce was a tapestry woven from different threads. Many were individuals with little personal choice in the matter, conscripted into service as a form of labor obligation to the state or the pharaoh. In other societies, this workforce included prisoners of war or those who were enslaved. They toiled in a challenging environment, facing the relentless sun, constant stone dust, and the ever-present risk of injury from a misswing or a shifting multi-ton block. Research into resting places near these sites suggests that many workers experienced physical hardship, with skeletal evidence pointing to the immense strain of repetitive, heavy labor and nutritional challenges that were part of life for the general labor force. Yet, to see this only as a story of hardship would be to miss the intricate social machine that made it all function. Skilled artisans, the master stonemasons and foremen, occupied a much different position. Their expertise granted them a higher status, better rations, and sometimes even the ability to earn wages. They were the ones who could read the stone, direct the work, and ensure the quality of the final product. This clear hierarchy was not just about privilege, it was a practical system of motivation and control. A skilled worker could aspire to a better life, while a laborer might hope for an extra ration of beer or a day of lighter duties. This created a social structure that, while deeply unequal, provided a framework for managing thousands of people over decades. The very longevity of these quarry sites speaks to a system that, for all its harshness, found a way to sustain its human engine. It was a society in miniature with its own rules, its own rewards, and its own methods of ensuring that the work, no matter how grueling, would continue season after season. This complex organization extended beyond the quarry's edge, influencing the very identity of the workers and leaving a mark that resonates through the objects they left behind. Stone was a currency as potent as gold or silver in the ancient economy. The control of a prized quarry was not merely about possessing a resource, it was about wielding immense economic power. A city that held the rights to a source of fine marble or a rare stone like Egyptian porphyry commanded both respect and immense wealth in the ancient world. This was because the stone itself became a form of high-value trade good, shipped across the known world. The very identity and prestige of a ruler or a state could be defined by the monuments they built, and those monuments required specific, often exclusive, materials. Owning the source meant controlling the supply of that prestige, creating a powerful economic and political advantage that could shape alliances and influence international relations. The financial engine of a major quarry was staggering in its complexity. It was not a simple matter of digging rock and selling it. The initial investment was enormous. The state or a wealthy patron had to fund the entire operation upfront, from building the access roads and worker barracks to forging thousands of specialized bronze and iron tools. This massive capital outlay stimulated a wide range of ancillary industries. Local metalworking shops boomed, constantly producing and repairing chisels, saws, and levers. The demand for transport created a parallel industry in shipbuilding, as massive barges had to be constructed to carry their heavy cargo. The need to feed and supply thousands of workers in remote locations fueled local agriculture and pottery production for storage jars. This created a powerful economic ripple effect, a web of interdependency that stretched far beyond the quarry gates. This vast industrial machine required a sophisticated system of trade and logistics to function. Blocks of stone were not just local building supplies, they were international commodities. In the Roman era, a vibrant and lucrative maritime trade developed, with ships crisscrossing the Mediterranean, their hulls filled with colored marble from Turkey, granite from Egypt, and limestone from local Italian sources. These materials were shipped to central distribution yards like the one in Rome itself, where they were sold to both state projects and wealthy private citizens. The cost was extraordinary. A single, large column of imported granite could cost the equivalent of a year's wages for hundreds of laborers. This trade established and solidified new economic routes, connecting distant provinces through a shared demand for luxury stone. Ultimately, the true measure of this industry's success was its profound and lasting impact on the broader economy. It employed a significant percentage of the available workforce, from the unskilled laborer hauling ropes to the highly paid master mason directing the work. The wages paid or the rations provided fed families and supported local communities. The taxes and tributes levied on the extracted stone filled the coffers of empires, funding not just more construction, but also armies, navies, and public services. The economic footprint of ancient quarrying was woven into the very fabric of society, demonstrating that these operations were as much about fueling an economy as they were about erecting timeless monuments. This financial powerhouse, however, would eventually face its greatest challenge not from a lack of demand, but from a changing world, as the very definition of construction and the materials that powered it began to evolve. The landscape itself became a permanent record of their ambition. Ancient quarries are not merely holes in the ground, they are vast, sculpted spaces where entire hillsides were systematically dismantled. This relentless extraction fundamentally reshaped local environments, altering the very flow of water and carving out entirely new topographies that still define these regions today. To power this industry, vast tracts of forest were cleared. The demand for wood was insatiable, fueling the furnaces that smelted metal for countless tools and providing the timber needed for sledges, barges, and the sprawling support settlements. This large-scale deforestation was likely one of the first significant industrial impacts on regional ecosystems, a reminder that our relationship with the environment has always been one of both dependence and transformation. Yet within this immense alteration, we also find a pragmatic form of intelligence, an early adaptation to environmental constraints. quarry sites were frequently chosen with a clear eye for efficiency, positioned as close as possible to natural waterways like rivers or the sea to avoid the monumental effort of long overland hauls. They learned to work with the land, not just upon it. This nuanced relationship is perhaps most beautifully illustrated by the afterlife of these sites. Many abandoned quarries found a second purpose, their deep excavations naturally filling with rainwater to become vital reservoirs for farming communities. Others were carefully terraced and converted into fertile agricultural land, a thoughtful recycling of an industrial site back into a source of life. The sheer scale of these excavations forces us to acknowledge a profound truth, that human industry has always left a deep and lasting signature on the planet. These quarries are not just relics of construction, they are a foundational chapter in the long story of our species' interaction with the Earth, a story whose next great shift would come from a new way of thinking, one that sought to replicate the strength of stone with entirely new materials. That deep, sculpted landscape is not just a relic, it is a living blueprint. The rumble of modern machinery in a granite quarry may seem worlds away from the rhythmic tap of ancient hammerstones, but the fundamental principles at work are direct descendants of those first innovations. Modern stone extraction, for all its diamond-tipped saws and hydraulic splitters, still relies on the foundational wisdom systematized by ancient engineers. The very first step in any quarry today is a geological survey, a high-tech echo of the ancient surveyor listening for the bell-like ring in the bedrock. We still seek out the same unweathered strata, avoid the same hidden fissures, and map the natural fracture lines to guide our cuts because the physics of stone have not changed. The controlled force used to split a multi-ton block today is merely a more powerful version of the swelling wooden wedge, a principle of directed pressure that remains unchanged for millennia. Even our logistical chains, with trucks and trains replacing barges and sledges, follow the same core logic, moving stone from the source to the site with an efficiency that would be deeply familiar to a Roman foreman. This continuity extends beyond mere technique into the very materials we value. The gleaming white marble of the Tennessee quarries that clad modern landmarks is prized for the same luminous quality that the Greeks discovered on Mount Pentelicus. The deep, speckled granite favored for corporate lobbies and memorials continues a tradition of imperial grandeur set by the porphyry and granite of Egypt and Rome. Our aesthetic standards for building stone were largely codified in the ancient world, creating an unbroken thread of taste that connects a pharaoh's obelisk to a contemporary city plaza. This is the true legacy of those early innovators, a testament to solutions so elegant and effective that they continue to shape our world, reminding us that the most enduring technologies are those born from a profound and intimate dialogue with the natural world. The true marvel of these ancient quarries lies not in the monuments they built, but in the minds that conceived the systems behind them. We have journeyed from the surveyor's first hammer tap to the final block loaded onto a barge, uncovering a story of profound human ingenuity and staggering organization. It was the seamless fusion of precise tool technology, masterful labor management, and deep geological knowledge that allowed civilizations from Egypt to Rome to overcome challenges that would still be formidable today. These were not random acts of brute force, but calculated, orchestrated campaigns that transformed entire landscapes. The methods they perfected, from splitting stone with wood and water to managing supply chains across continents, did more than erect pyramids and colosseums. They established the foundational principles of engineering, logistics, and project management that our modern world still relies upon. So the next time you stand before an ancient monument, look past the sheer scale of the stone. See instead the intelligence embedded within it, the echo of thousands of coordinated hands and brilliant minds working in concert across the centuries. Their legacy is a testament to what humanity can achieve through perseverance and collective effort. If this journey into the past resonated with you, please support our channel with a like and subscribe for more explorations into the world's great historical mysteries. We would love to hear your thoughts, so share which ancient technology fascinates you most in the